On to light acting as a wave. Though Huygens' observations made the case for light acting as a wave, Isaac Newton still disagreed, and that's a big deal. So until 1801, the English physicist and physician Thomas Young created the double-slit experiment. Here you can see the difference between a mechanical wave and a light wave. A light wave is the oscillating electric field and the oscillating magnetic field, or the B field, oscillating perpendicular to each other. So it's really this messy thing that we saw before when we talked about polarization. So for Thomas Young's double-slit experiment to work, we have to have light interacting with something really small. In this case, very closely spaced and narrow slits in a material. So you have light coming in, you have these narrow slits in a metal sheet, and then you have a screen or a wall some distance away. The light has to be coherent. That means the light must be in phase, or a relationship for the phase exists. This allows for constructive and destructive interference to occur. Right? Remember, constructive interference, crest meets crest, gets bigger. Trough meets trough, gets bigger in the opposite direction. Meanwhile, crest meets trough, you get the destructive interference. The idea is that as light passes through each slit, it'll be diffracted into semicircular waves interfering with each other. Okay. When we look from a little bit farther out, we see the waves coming through and interacting with each other. So we're getting our interference. And then over here on the wall, we're seeing this interference pattern of these light areas and dark areas. We call the light areas light fringes and the dark areas dark fringes. Dark fringes are where the destructive interference is happening. Crest meets crest. The light areas are where constructive interference is happening. Crest meets crest. So let's look at this another way. If we have light coming from this top slit, it's going to travel this path. If we have light coming from the bottom slit, it's going to travel this path. Which one of those traveled farther? Well, you can see, I think, by looking at it, but if I draw a line straight down to be perpendicular to my second path length, then my angle here is the same theta as was given to me from this center line. So the angle from the center line to our dark spot over there. What we call this little piece right here is called the path length, or the path difference. The path length is just the full length that the light would have to travel to get to an area of interference. The path difference is this little extra bit that has to be traveled by the second wave. Of course, if we switch things around and we were looking down here, now the top one has a longer path. Right? So this path difference is really going to determine whether or not we have destructive or constructive interference. So if the path difference is a fraction of your wavelength, like half of a wavelength, you're going to get destructive interference. Meanwhile, if it's an integer, like 1 wavelength or 2 wavelengths or 5 wavelengths, then you will get the bright constructive interference. So, destructive interference occurs because one path is half a wavelength longer than the other. The waves start in phase but arrive out of phase. Constructive interference occurs here because one path is a whole wavelength longer than the other. The waves start out and arrive in phase. Alright, moving on. So here is the double-slit experiment from yet another view. So we have the semicircles coming out and then interacting with each other and then hitting the screen. And when it hits the screen, there's a pattern of light and dark fringes observed on the screen. The centermost, or M, or as we're going to call it soon, N equals 0. This will be the maximum intensity. Meanwhile, as you go farther and farther away from that center spot, the intensity of these bright fringes is going to decrease. And that's because your intensity of light decreases as you get farther and farther away from it. That's why stars in the sky are dim, because we're really far away from them. And the sun isn't that far, so it's pretty bright. Here it is yet again. Same situation happening. We have our intensity line right here, so our maximum intensity is shown here, and then this center spot is going to be our maximum intensity. Each of these bright fringes are areas of constructive interference. The dark fringes are destructive interference. So from this, we were able to get an equation, and that equation in your data booklet is going to look like this. S equals lambda big D over little d. Big D on top because it's biggest. So S is the distance from the maxima to the light fringe in question. So the distance between each of these two fringes, or three fringes, that is your S. N is the number of constructive points from the center. So remember in this slide right here, I told you we were going to call these N, and that's just because N is the number of fringes from the center. I think it makes it a little bit easier to remember because you have enough to remember. So if N equals 1, then we would just use 1. If N equals 2, then we would plug 2. N does not show up on this equation, but it's just multiplying this whole relationship. So you can think about it as over here or in the numerator. Big D is the distance, the big distance from your slits to your screen. Little d is the distance between the slits. Meanwhile, lambda is still wavelength of light. How to determine the path difference for waves traveling from two slits. We're going to cover that in the next